we take a look at another well-known problem involving matrix valued optimization variables, namely the low rank matrix completion problem. Now, to motivate the problem, let me first discuss the idea of recommender systems, which are basically algorithms that are responsible for making recommendations. You must have already seen recommendations on all sorts of e-commerce websites. For instance, if you use Amazon, then you must have seen various products being recommended to you. So how are these recommendations generated? There are basically millions of items and millions of users, and it is all not as simple as suggesting the popular items. In fact, if you look closely, these recommendations are specifically tailored to your history, to your purchase history. And not only that, they will also recommend items that you did not, they will not recommend items that you did not like. Although you have bought them, but you may not have necessarily rated them. So they know which items you will like, even though you necessarily did not give them 5-star or 1-star. And the same happens with all sorts of websites like YouTube. Again, even if you do not rate the videos that you watch, they will know which are the ones that you will like and recommend only those. And the list of platforms using recommender systems is huge. For instance, this is the recommender system used by Google Play Store. And then this is the recommender system used from Netflix, which I think must be one of the most sophisticated systems in the industry. Now, as you may know, Netflix initially started as a movie rental company. That is, not all movies were available online, so you could request them and they would mail you the CD. So that was in early 2000s. Then slowly they started serving more and more content online. So at that time, Netflix had a good collection of movies, but it was not an exhaustive one. In fact, it was unique at that time because it had so many relatively unknown movies and TV series that otherwise no one would go and rent. So because many of these movies on the platform were not very popular, people obviously had difficult time choosing what to watch. So Netflix had a recommendation system at that time that they were interested in accurately predicting the movies that they think the users would like, and based on each user's personal preferences. Now this was still 2005, 2006, and much before the AI was much more like sophisticated and widespread. So Netflix had a rating system where each of the users could rate movies from 1 to 5-star. So if you actually arrange the movies on the columns and users along the rows, then you can view the ratings collected by Netflix as a matrix. Note that this matrix was largely empty because most of the users had not seen most of the movies. And the goal of any recommendation system is basically to estimate the missing entries, these question marks, based on the given entries. A recommendation engine must therefore try to predict the user ratings based on what movies the users have seen and how they have rated those movies or some of those movies, and how the other users who have watched the same movies have rated those movies. So in 2006, Netflix announced a prize of $1 million for the algorithm that would be able to improve their existing recommendation engine, which was called CineMatch, by 10%. So that was the goal. And they released a lot of ratings data matrix, a large rating data matrix that must be completed. Now 10% may seem like less, but Netflix engine was already state of the art, and actually 10% improvement resulted in huge improvement in the kind of recommendations that were being generated. So that competition turned out to be a big success and spurred a lot of research in matrix completion. In fact, Netflix's own CineMatch algorithm was beaten in just 6 days of the announcement of the competition. And the overall competition received 44,000 entries. Further, it took 4 years for any of the teams to improve the CineMatch algorithm by 10%. And the winning team consisted of a collaboration of lots of researchers from AT&T and Yahoo. More importantly, there was a surge in collaborative filtering papers, and a number of theoretical developments also occurred around that time. Let us then move on to discuss the problem formulation of matrix completion in more detail. If you look at the Netflix data, it contained ratings given by some 500,000 or so users and about 20,000 movies. So the question is that given all these ratings, how do we fill in all these blanks? By the way, Netflix no longer has this 1 to 5 star rating system, but when it had, this is what the stars looked like. One important point to note is that if you are given an arbitrary matrix with missing entries, there is no way that you can complete it. That is obvious because you have no information about those entries, and especially if they are allowed to be completely arbitrary. So the completion is only possible if there is an underlying structure present in the matrix. And that structure would basically be used to render the problem solvable. So the basic idea behind matrix completion is the underlying assumption that the full matrix that is given to you or that is unknown is actually low rank. In other words, if you have a k cross n matrix, ratings matrix, then although it has k times n entries in total, but it is really a product of k cross r matrix and another r cross n matrix, where small r, which is the rank, is much smaller than k or n. So with this, you can see that intuitively the number of entries is only r times k plus n, which is much smaller than k times n. And while completing an arbitrary matrix, therefore, although completing an arbitrary matrix is impossible, completing an low rank matrix may actually be possible, because now we could be given much more number of entries, or we could be given much more number of measurements than the number of entries that we are required to estimate, or the number of optimization variables. So what is the intuition behind the matrix being low rank? So why do we say that the rating matrix is low rank? The reason is that movie ratings are not really arbitrary, but in fact they are highly correlated. Actually, if we properly permute the columns and rows of a matrix, of a low rank matrix, it would look something like this. So here the color denotes the ratings. So they say, you could say that blue is high rating and yellow is low rating. And the key to notice here is that if you look at any two consecutive columns, so let's take a look at any two consecutive columns which correspond to two movies. Now those movies, this matrix being low rank is saying that those two movies are such that there are lots of users, and in fact all the users have rated those movies very similarly. So for example, you could take an example of two action movies, very similar action movies, part 1, part 2, and then some users like both of them, while there are some users who hated both of them, while there were some users who were okay for both of them, and so on. So both the movies would be rated very similarly across the entire spectrum of users. And such a behavior occurs across all sorts of movies, sports movies and all sorts of movies. So there are many sets of movies which all elicit similar responses from various groups of users, various types of users. And conversely, if you look at two users, say two like-minded students of IIT Kanpur, they would have a very similar movie preference. For instance, they may all like Hollywood movies and they may all hate Indian movies and so on. So in summary, the low rank assumption is very intuitive for the ratings matrix because it reflects what we know about user preferences and movie preferences. And the same actually idea applies to products when we are buying products and so on. This has actually been observed in reality. The low rank structure has actually been observed in reality. So next, let us mathematically formulate it. Our goal is, so let us say that the X is the unknown but complete matrix. We don't know it. And the ratings are given in a partially complete matrix M. So there is a matrix M on which ratings are given. In the matrix N, only some of the entries of M denoted by this set omega. So omega is the set of all I comma j, which are the corresponding entries which are given. And then what we want to do is find the smallest rank matrix X. We want to find the matrix X with the smallest rank such that X agrees with M on those I comma j, which are the ratings that are given. So this formulation also makes sense. We are essentially looking for the smallest rank matrix that has the given ratings for user movie pairs. Now there is a complication with this formulation, which is that rank is actually a non-convex function of X. It is the number of non-zero singular values of X. So how can we approximate it with something that is convex? Note that we have encountered a similar problem before when we were looking at compressed sensing. There we wanted to find a vector with fewest non-zero entries, but instead of that we considered the sum of absolute values of its entries. In a similar way, here we want a matrix with fewest non-zero singular values. So we can approximate it, the objective, with the sum of absolute values of the singular values. Now of course singular values are already all non-negative by definition, so the relaxed problem entails finding X such that its sum of singular values is minimized. So the nuclear norm of matrix X, denoted by this subscript star, so this is the nuclear norm of the matrix X. It is the sum of singular values of X. And hence we can replace the rank in the objective with the nuclear norm of X, which is a convex. It is a norm, so it is convex. So nuclear norm can be thought of as the L1 norm counterpart for matrices. It is in fact the L1 norm of the vector of singular values and therefore analogous to the actual L1 norm that we have used. So actually the L1 norm minimization problem and the nuclear norm minimization problem, they are sisters. They are very, very related to each other. Many of the results developed for L1 norm minimization apply to nuclear norm and vice versa. So before proceeding, let me just express this constraint compactly. So we can say that the projection of M minus X, P omega is the projection of M minus X over omega is 0. So here the projection operation, what it is doing, it is taking all the entries in the matrix M minus X and outputting only those entries whose indices are in the set omega. In other words, those entries for which Mij is given. And it is saying that for those entries, Mij is equal to Xij. So this is just P omega M minus X equal to 0 is just another way of saying the same constraint. Similar to lasso, we can also consider the penalized formulation where we minimize the fitting error plus lambda times a nuclear norm penalty. So different from the previous problem, here we are allowing slight deviations in the given ratings. So assuming that the given ratings do not actually represent what the users feel about the movies, but they are noisy. You can think of them as noisy ratings. And the formulation will output clean ratings. And as you can see, this is also a convex problem because the first term is quadratic and the second term is the nuclear norm, which is convex. And just a remark that this class of problems can usually be solved using various stochastic gradient descent algorithm and its variants. Lots of variants are there. And in fact, it can also be formulated as an SGP, this particular, but solutions using SGD, stochastic gradient descent, are usually much faster. Finally, we come to the hybrid problem. So this is called the robust PCA problem. Here, you are looking at an example of foreground background separation. So you are given a video, say from a CCTV camera, where the background is still because the camera is still, but the people which constitute the foreground, they keep moving. To separate the background from the foreground, you can assume that the background video, so if you vectorize the frames of the background video is basically the same frame repeated many, many times. So it can be basically represented as a low rank matrix. And the foreground has no such low rank structure. It is basically a sparse matrix because there are only few people. The foreground is much sparser than the background. So the problem becomes a hybrid problem of splitting a given matrix into the sum of low rank and sparse matrices. This is also called the robust principal component analysis (PCA) problem. And of course, this is not perfect because in the background things could also be moving. For example, in the top figure, you can imagine that the escalator is actually moving, but it should ideally be part of background. But here it is being, some part of it is being detected in the foreground also because it is moving. So how do we formulate the robust PCA problem? We can formulate in a very similar way. We can say that M, which is a given matrix, is a sum of low rank component L and a sparse component S, and then we can minimize the fitting error norm square plus lambda times the nuclear norm of L, which will encourage that L is low rank, plus a penalty on the L1 norm of the vectorized version of S, which will encourage that S is sparse. The matrix S has sparse entries. So as you can see, this is also a convex problem because the first term is quadratic and the next two are the norms, which are also convex. And again, in this case, many SGD, stochastic gradient descent variants have been used to solve it, and there are many algorithms at this point. So this was all about matrix completion and related robust PCA problem.